And first, since I'm pretty sure no one actually knows what InfoStellar is, it's a very new company, I'm going to give a brief explanation of what we do. And so I think seeing the graphics will make it much easier to understand, so pardon some of the marketing that's in this marketing video. And so
Stellar Station is a platform that enables antenna sharing for satellites. The advantage is that free antenna time.
And so we're creating a network of antennas all around the world that can then communicate with satellites. The problem with satellites is that they're always moving around the Earth. And so if you want to be able to communicate with the satellite, it has to be over a specific antenna, which only happens, for example, for 10 minutes at a time. And so if you would like to be able to keep on communicating with your satellite, you need to have antennas all across the world, and hopefully in one network, so that you don't have to worry about where your satellite is. You can always be communicating with your satellite using all of these different networks. And so this is sort of the idea. And so as you can see, we're trying to create this sort of communications platform. And because we're creating a network, latency matters a lot. And so tracing is also very important for us, so we can debug any issues and make sure that our network is as fast as possible. So I can even show just a little bit about what the site looks like. And so this is Stellar Station, which is our product. And basically, you can see these are all the satellites that we're currently tracking, and these are the antennas that we have on the system right now. So anytime a satellite is over the antenna, we'll be able to download its data. And this is a list of satellites. And for example, you can go to a satellite and look at the data from that satellite. Next time it goes over one of our antennas, we'll get new data. And so we just have this network of antennas in various locations connected to the system. And so, as you can see here, so to render this page, we have a microservice architecture at InfoStellar. We have split responsibilities. For example, there's a server for user credentials. There's a server for computing the time that a satellite will be over antennas. And we have various services. In this page, what was required was to check the logged in user, get the permissions for that user, and then get the satellites that they have access to, show the list of satellites, and also get the upcoming time periods of communication, which we call pass. So get the upcoming passes for the satellites they have access to. And when we render that as a trace, it looks something like this. And so Adrian first showed some example of you have a web request and then various different aspects of that request. And so here, get amateur homepage is the request to get the data for that page I just showed you. And so you can then see when we're getting the information for the user token, which is all the ACLs and the information about the user. We make a request to the user service, which also makes requests to the database. And these are all the timings of the individual components. And then there's also a request to find all the counts of number of plans that have been completed, and also the positions of the satellite to render on that page. And so even when you have very many different servers involved with a single request, you can have one view where you can see all this different time spent in each service. And so just to give a brief overview of what technology we are using to achieve this. So we are tracing servers. I think this is very common for many services, especially even consumer applications. You have an app, it has to get data, render a page, users interact with it, they'll render a new page and maybe do some different interactions. And so most people have this problem with tracing servers, I think. And at InfoStellar, we're using Google Cloud Platform and Kubernetes for managing our servers. Our servers are written in Java, we use Armeria, which is line server framework, along with gRPC, which is a way to communicate between different services. It makes it very easy to write the code to communicate. And then we also use this thing called Dagger, but I won't go into it. And so for Java, we use this tool called Brave, which is part of the Zipkin project. And Brave comes with lots of code to be able to instrument. Instrumenting is basically just annotating the times when something happened inside your services. And so, for example, Brave has instrumentation to annotate when a gRPC request started and ended, or when a MySQL database call started and ended. Even, maybe not Brave, but I think there's also instrumentations for Redis. And this PubSub, there's no official one yet. We have to implement it ourselves. I'll talk about that a bit later. And we are also using Stackdriver Trace, as you mentioned. But so instead of using OpenCensus and some of the other Stackdriver libraries, we use Brave and Zipkin for instrumentation. And only the final ingestion happens to Stackdriver Trace, and then we can view it on their UI. So it makes it very easy because we don't have to manage infrastructure for Trace. And Adrian showed you the list of sites pages, but all of the details about how we're doing this is listed on the sites page. And so one interesting thing, and so I'm also just going to be mixing in my observations as I've been implementing tracing into this presentation. And so one thing here, you'll notice these gaps over here. And these are what we call untraced time. And so basically, ideally, you know what is happening at any given point of time of a request, but that requires perfect instrumentation. So we saw instrumentation of gRPC, we saw it of MySQL, but even then, there might be bits that are not instrumented. Maybe even we do not instrument the TCP warm-up time, or maybe there's some business logic that isn't instrumented. For example, here, actually, I don't know what's the exact reason. I can speculate. There is actually a code that we do to verify the Firebase token. We use Firebase for authentication. We did not add instrumentation for that yet. That's probably in there. There could be some TCP warm-up time. Unfortunately, we don't know, and I feel that untraced time is sort of the bane of tracing. You can do tracing, but until you have as much instrumentation as possible, you will not ever be able to get the full value because you'll still have these times when you don't know what actually is going on. And so one way that might help is to have method level instrumentation in your code. Method level instrumentation can be very expensive because there's so many methods, but maybe only running this in for X% of requests or in an alpha environment or something like that can try to help understand why some of your time is untraced. And so for us, the feature work is to be at method level tracing of all of our asynchronous code, we use something called producers. I think there's similar concepts in RX Java and stuff too. But for any unit of computation in your server, if you have tracing, it can help debug instrumentation issues. But yeah, so that's tracing services. And I think tracing servers is very common for everyone. What's probably more unique to InfoStellar is that we have a global network of ground stations. And as I said, we're making a network. Network means that latency is a problem. Latency being a problem means we have to be tracking it. And tracking it means we need to do tracing. And so definitely tracing from the ground station to the user is very important to us. And so basically when communicating data between the user and the satellite, the flow will usually look like this. We have a device called the StarPass, which is connected to the antenna. And these will be in locations like South Africa or United Kingdom or anywhere around the world. And these are outside of our network. Users will also probably have an API client in maybe in their Amazon service or even on their in-premise computer or something, but this API client is also sort of outside of our network. And then in between, we have our infrastructure running on Google Cloud. We use PubSub. PubSub is similar to Kafka or Rabbit and Pure, any of these messaging things. It's Google's managed message queue. We use PubSub to transmit to one of our own API servers, which is serving a gRPC bidirectional stream for the API client. And so one key thing Um, so one key thing to keep in mind here is that we have control of StarPass. We have control of the streaming API. Unfortunately, we don't have control of Cloud PubSub because it's a managed service. We also don't have control of the user's API client because it's their code. And so this means, as I said, untraced time is the bane of all tracing. But we will have untraced time, and we're just going to have to make the best of it. It's the trade-off of using managed services often. And so we'll see sort of some of the workarounds we do to get around this, as well as just some of the compromises we make. And so the first step of tracing is annotating spans. So it is marking the time that something happens along with some name. The name can be really anything. It could be the name of the MySQL query. It could be name of an RPC method, an API method. And then it's at start and end times. And that's basically what a span is. In Java, we use these libraries called Armoria, Zipkin, and Brave, which provide automatic tracing of gRPC. And we also, on the ground station side, on the StarPass, our software is written in Go. And there we're using libraries called Open Tracing and its gRPC integration called OTgRPC. Another aspect of tracing is ingesting spans. And so you have this information, time, name, that has to go to some storage so that a user can later go to your UI and look at the span, look at the trace, and see how things are going. And so for us, we're ingesting spans directly into Stackdriver Trace. And Stackdriver Trace has an API that's accessible anywhere. It's just on the internet. And to do this, we're using Zipkin to annotate our spans on the server side. And there's a module called Zipkin GCP, which just converts from Zipkin to Stackdriver. So that's easy. On Go, there was no such library to convert from open tracing to Stackdriver, so we had to write it ourselves. Some of the details of conversion can be a bit tricky. We did run into that. But what's great about this is it works perfectly from both the cloud and the edge. Because even though the edge are ground station computers, the StarPass is not in Google Cloud. It's not on any network we control. Since Stackdriver Trace is available from the internet, we can ingest spans all the way from the edge with no problem. And so this has made things very easy for us. And then the third aspect of tracing is propagating context. And so Adrian mentioned B3. And so basically, you have a whole trace which has an individual ID. So this whole thing I showed you here is a trace. And so every single blue box in here has the same trace ID associated with it. Well, each of them also has a span ID to identify themselves uniquely within this trace. And so it's important that when the server gets getAmateur homepage, it generates a trace ID. But this guy, the user service, also has to know what the trace ID is, or else the spans cannot be connected. And so that's called propagation, the way that one server notifies another server of at least the trace ID, also span ID, so you can show a nice graph of the parent-child relationship, though it's not as critical as the trace ID, because otherwise you wouldn't even be able to show them here. So it's important to propagate these IDs to other servers. Most instrumentation takes care of it automatically. For example, Armoria Zipkin, if you use it, you don't have to worry about propagation. These IDs are automatically added to HTTP headers and retrieved from HTTP headers on the other server. When we were trying to trace PubSub, as I said, from our edge, we're using PubSub as the transport. I couldn't find any official libraries to do propagation for PubSub. And so we had to implement code to read and write the same V3 headers and values as PubSub message attributes. It's not so hard. But even then, even though it seems simple to just set these values as attributes, propagation is sort of a complex topic. And actually the first version of the code forgot to use the official trace ID, XB3 trace ID, XB3 span ID names. It accidentally used trace ID and span ID. And so that, since didn't match, the propagation didn't happen. And so the spans from the ground station and the servers could not be linked. And so even such a simple concept, when you have to write it, it's very easy to mess it up because it's a very hard concept, I think. And so then the final thing, as we're trying to annotate our edge tracing, we run into this problem of what is a pub sub spam really? And so I think the tracing model was originally designed for a system with only unary RPCs. You send a request and you get a response back. So send request, you might send another request within that, send a database, get a response, send request, response, but there's always a request and a response. And those are the edges of the spams, of the blue boxes here. But with PubSub, with message queues, that's not true anymore. There's no response, there's only publishing messages, and someone else gets it. And it's totally independent. And so it's hard to sort of say, is that even a parent-child relationship? How are you supposed to show it on this view? And so, and I don't know if there's a best answer for this yet. I think this is still an open problem in the tracing community. But for us, basically when we look at what exactly PubSub is, it's a combination of two RPCs. One is a unary RPC, request response. One is a streaming RPC for just receiving the messages on the other side. And so when you do PubSub, you publish the message. There will be some propagation delay between the message being published to the subscribers, completely arbitrary, depending on load and whatnot. There could be lots of delay, and we don't even have any good prediction. Well, on the same side, the person that's receiving the message has a streaming RPC. They're continuously listening for new messages to come in. Another unique thing about especially Google Cloud PubSub, this might not happen in Kafka and whatnot, but Google Cloud PubSub has an at least once delivery model, so you might even get the same message twice. And that makes tracing even weirder, I think. But and then we decided to take the model of the call to publish is a spam. The receive the message is also processing the received message is also a spam. There's no parent-child relationship. We just see the blue boxes on the trace and deal with it. And so one other thing, so again, since there's no server and client, there's only publishing and receiving, totally independent. In normal tracing, you have spams, blue boxes corresponding to time happening in a server, and then also time happening within the client that's talking to that server. It can be useful to have server spams, I found, because generally it's easier to guarantee your servers are properly instrumented than clients. You tend to have less control of clients, and so at least if you have server spams, you can get some of the benefits of tracing. And so with PubSub, we found that the lack of a server spam is causing us a problem. I mean, for example, we even had a bug with our propagation. And so if we were only relying on client spam from the edge, we would not have any tracing at all at that time because there would be no spams at all. And so we decided that we can synthesize a server spam for publish based on the publish time, which is when Google Cloud PubSub received the message, and our current time. And so this is sort of a simulated spam. It's not ideal, but it does sort of capture the time properly. And it helped us actually. And then finally, when handling the message, we get a message from the stream. And so what we do is we create this server spam for publish based on the publish time included with that message. This is a synthetic spam. Our server has nothing to do with publish. We create the spam anyways because we want to make sure to record it. And then we create another server spam for received message to actually document the processing of that message. And so we just assume that the end of the publish call is this current time. I don't know if that's correct. Maybe publish should spam the whole processing, but this seems to work fine in our usage. And then eventually finish the received message spam when the message is done processing. Another issue we ran into is the fact that this is a long-running stream. So the API client can connect to our server and just connect forever, continuously streaming satellite data whenever it's needed. If you model a long-running stream as one trace, that seems ideal because then you can compare the time between messages. But if it's an infinitely long trace, that means your trace will just last forever and get full of spams, and that's not very useful either. And then we use one trace per message. It would help in some cases if we use one trace for the stream, But in the end, it's also quite impractical, and so we have to compromise and just use one trace per message. And the end result, what we see is, we see the publish. This is our synthesized span for the, this is actually this is the client span. So this is where we've already fixed the bug. And so this is the client span for, this is interesting. So this is the client span. This is the time the client saw when it was publishing the message, 80 milliseconds. Unusually enough, when we created our synthesized span using the publish time that Google reported to us, it actually started all the way over here. And then finally we have our span for processing the message. As you'll see, all of the time here comes after our synthesized span for the publish. And so this was actually really enlightening for us. We were surprised. We thought publishing should be very fast. There might be some propagation delay until the subscriber receives it. But what we found was, for some reason, there's tons of time between when we start publishing to when Google actually records the message as published. And 80 milliseconds is a long time for publishing messages. And so we were surprised. But luckily, this gave us a clue in that it was obvious that it's the actual publish RPC, the Unity RPC, where we're sending a message to Google that was slow. Why could that be? So it did narrow down our scope for debugging. And what we realized then was, and then so we thought maybe it's because of the interval. We tried different publishing intervals. First, we were just trying every 1 second, and that's when we saw every published RPC take 80 milliseconds. When we tried reducing it to 10 milliseconds, every published RPC started taking only 5 milliseconds. So there's huge correlation between the published interval and the time of that span. And it was very helpful for us to know about this. And also it made us happy because, and then this 1 second thing was sorted for testing. In practice, we're going to be probably seeing more in the range of milliseconds for our published interval. And so as long as the added latency of pub sub isn't so large, our network latency should also be manageable. And so at this point, we were sort of happy, especially with this discovery. And this was very experimental along the way we finally got here. So I tried to clean up some code, changed some of the code related to propagation and whatnot. And what I ended up with this, where I accidentally seem to have introduced a bug where now all spans have the same trace ID. And so this is probably an hours long trace of all the spans in the server. And so even now, because I have to write my own code, and since it's very tricky to get these things right, especially the propagation of the context and whatnot. And if you have just one bug, everything just gets destroyed. And so I know my friends at Line have run into this too, but tracing is definitely still not a very easy problem. And it will be nice when there's even more libraries for these special use cases to make sure that people can use the code rather than having to run through these bugs and fix them. On the flip side, I now know that maybe using one trace per stream is reasonable. The Stackdriver does seem okay showing me hundreds of spans for one trace. So that was surprising. And so now I do want to close with talking about the tracing ecosystem, especially when going through this project. We were tracing both the Java servers and the Go client code. And so I found that there's so many different ways to do every single aspect of tracing. And so first, of course, there's programming language, which each has to have an implementation of tracing. Then there's the instrumentation library. Each language would probably have multiple libraries for instrumentation. There's trace targets like gRPC and REST API. They might be more common. There's less common ones like PubSub. There's propagation, B3, but also Stackdriver has their own propagation format. gRPC has its own propagation format. As soon as you change the propagation format at one point in your system, your tracing fails completely because then the trace cannot be connected. And then there's also many ways to do storage. You can use Zipkin server, which is what Adrian just demonstrated. You can use Stackdriver trace, which is Google's managed thing, X-Ray for Amazon's managed thing. And all of these are sort of independent components. And when we decided to add tracing for our Golang code, what we found was this. Zipkin works well with B3 and Zipkin server on Golang, but did not have any support for gRPC or Stackdriver storage. OpenCensus, which is Google, or I guess run by Google, has trace. Oops. No one has support for pub/subs, right? This was supposed to be great. OpenCensus includes gRPC trace target, but it only supports gRPC propagation. It has a storage driver for Stackdriver, and then OpenTracing supports tracing of gRPC, but no. It also has support for propagation of V3, but no support for storage of Stackdriver. And so, and then we leaned towards propagation, because if you screw up propagation, your tracing is dead. And we saw that OpenTracing supports gRPC as a target of tracing and V3 propagation. So we went with it and wrote our own Stackdriver code. But it was quite complicated going through this ecosystem. And especially because we use Zipkin on our server side, it was hard to grasp some of the concepts of OpenTracing. So just last week, I finally went to Zipkin Go and implemented gRPC as a trace target. So that'll be merged soon, I think.
Thank you.
And so then there'll be then there'll be there'll be 3 purple things. Eventually, maybe we'll need to implement a purple for Stackdriver. And then if everything can happen with one library, it's much easier to get started. Okay. And so yeah, that's my presentation. And so if you have any questions, feel free to email me. I'm rag@istellar. And yeah, we still have 2 minutes. If anyone has any questions on this presentation. Otherwise, we'll... Okay, thanks everyone.